All right, let's do this. So we are told that we have a 40 milliliter sample of 0.1 molar nitrous acid, and it's titrated with 0.2 molar potassium hydroxide. And we are asked to calculate the volume required to reach the equivalence point, the pH after adding 5 mils of potassium hydroxide, the pH at 1/2 the equivalence point, and then I've gone ahead and added in one extra, which is determining the pH of the solution at the equivalence point. So what I would like you to do is to, as I'm going through and working through this problem, try to do each of these parts yourself. So you could even pause the video now and work on part A. But then as I'm going through the rest of these, I'm not going to pause each time and ask you to pause the video. I'm just going to trust and hope that you do that yourself as we go from A to B, and then from B to C, and then to D, that you will pause it and try to work each one out for yourself. I think it might be easier doing it that way than trying to do all 4 of those parts initially. I think it'd be easier for you to try part A, watch me do part A, and then try to do part B yourself, and then I'll do part B, and so I think it'd be a little bit easier. So on this first slide here, we're going to go ahead and do, I think we'll do just part A here. So in part A, we are asked to find the volume required to reach the equivalence point. Now if you remember, the equivalence point is where the concentration of H plus and the concentration of OH minus are equal to each other. And actually I shouldn't say that. It's where the amount of acid that we started with is equal to the amount of base that we put in. Technically speaking, these won't actually end up being equal to each other. Since we have a weak acid here, we'll end up making a weak base, which will throw that off. So it's better to say the number of moles of acid that we added is equal to the number of moles of base. And actually I said that backwards. The number of moles of acid that we started with is equal to the number of moles of base that we added. So that is the equivalence point. So what we need to do is we need to figure out essentially 2 things. Number 1, how many moles of acid did we start with? And then number 2, how much of our titrant do we need to add to get that number of moles? Because again, by definition, we need the same number of moles. So if we can work out how many moles of acid we started with, we can use our concentration for our titrant to work out what the volume of potassium hydroxide we would need. So we're told here in the problem that we have 40 mils of a 0.1 molar nitrous acid. Now, if we have 0.1 molar nitrous acid, what that means is we have 0.1 moles for every liter. That is literally what molarity means, the number of moles per liter. So we have 1/10 of a mole per liter. Not only that, we are told that we had 40 mils of this. So if we multiply the volume that we used by the molarity, and we will need to change this to liters. So we have 0.04 liters times 0.1 moles. That will give us, would that be 0.004? Don't trust myself to do math in my head. Yeah, 0.004. Moles of the acid. I'm just going to call it acid instead of writing out the nitric acid, or sorry, nitrous acid. So that's the number of moles of acid that we started with. So now we need to figure out how many mils of this 0.2 molar potassium hydroxide will we need to get the same number of moles. Well, if we need 0.004 moles of base, and we know the concentration, we can essentially do the kind of the opposite of what we did in the first part here and say, well, if I know I have this many moles of base, I can divide that by the molarity, and that will get me 0.02 liters of the KOH, of the base. So I will need 20 mils. Now, some of you might have been able to do that math in your head, just from looking at seeing that the concentration of this solution is 2 times the concentration of this one. So you would need 1/2 of the volume that you had, but I wanted to go ahead and work through all the math here because the concentrations aren't going to always work out quite so nicely like that. So this is the volume of base that we need to add to reach the equivalence point. After we've added 20 mils of the KOH, we will have reached the equivalence point, which, by the way, at the equivalence point, therefore, we would be at a volume of 60 mils. Because we started with 40 mils of the acid, we added 20 of the base, and so therefore, at the equivalence point, we will be at 60 mils total volume. And that'll come in handy later. All right, so that's part A. Part B asks us to find the pH after 5 mils of KOH is added. Now, the first thing we're going to ask ourselves here is, what region are we in? What region of the curve? Because remember, the region of the curve will determine the method that we use to find the pH. We know we're not in the initial phase because we've started adding the base. We can only treat it like a weak acid only if we haven't added any base yet. We know we've added 5 mils of the KOH, so the question becomes, have we reached the equivalence point yet? Well, thankfully, in part A, we figured out that we needed to add 20 mils to get to the equivalence point, so the answer is no. We are not to the equivalence point yet, which means we are in the buffer region. We are in the region where the solution, where the titration is acting like a buffer. So we need to figure out what is our concentration of our acid, what is the concentration of our base, and plug those into the Henderson-Hasselbalch. Now, because these different sections build on each other, some of the stuff that we need to solve this has actually already been worked out for us. So, for example, one thing that we'll need is the initial amount of acid that we started with. And in part A, we worked that out. It was 0.004 moles. So we're starting with 0.004 moles of the acid. But we don't have that right now because we've already added some base, and it's going to consume some of that. So what we're going to do next is figure out, we added 5 mils. We know what the concentration is. How many moles of OH minus did we add in there? So, let's see, 5 mils would be that many liters. And we know that for every 1 liter, we have 0.2 moles. So if we do that math, we added 0.001 moles of the base, the OH minus. So what stoichiometry tells us then is that all of these are going to react with our acid and turn it into its conjugate base. So we're going to have 0.004 minus 0.001 which is going to give us 0.003 moles of our acid left over. And this 0.001 moles of base just didn't disappear. It converted 0.001 moles of the base, or sorry, 0.001 moles of the acid into its conjugate base. So then at this point in the titration, we also have 0.001 moles of the conjugate base. So this was the strong base up here. This is the conjugate base here. Essentially, however many moles of strong base you put in, you create that same number of moles of the conjugate base, and that will always be the case. Okay, so we could theoretically at this point work out the number of liters of solution that we have and find the molarities and plug those into the Henderson-Hasselbalch, but we can also just plug the number of moles in. That will work just fine. Since they both are in the same solution, the volumes aren't different, it's just extra math. And so we're just going to go ahead and plug in the number of moles into the Henderson-Hasselbalch. So, but before we can do that, I do actually need to look up the Ka of nitrous acid, because I need the pKa. So let me find that real quick. Looking for my Ka's. There they are. Okay. So nitrous acid has a Ka of... Where did you go? There you are. 4.6 times 10 to the negative 4. Which means that its pKa would be negative log of 4.6 times 10 to the negative 4, 3.34. Right. So then, the pH of my solution is going to be 3.34 plus the log of the base over the acid. So 3.34 plus the log of 0.001 divided by 0.003, which is 2.86. All right. So, part C here is pretty straightforward. It just asks what is the pH at the 1/2 equivalence point. And if you remember from the previous slides, at the half equivalence point, all that means is that we would have 0.002 of both of these. We would have equal amounts of both acid and base, which would turn this whole thing into 0. And so the pH would just be equal to the pKa, which is 3.34. All right. So that leaves us with the last part here. Determine the pH of the solution at the equivalence point. Now again, thankfully, we have some data from earlier sections of the question, so we don't have to start from scratch here. If we did, we'd be doing a lot of work. But we already know from part A that at the equivalence point, we'll have a volume of 0.06 liters, and we will have 0.004 moles of the conjugate base present. So we have a volume of 0.06 liters, and we have 0.004 moles of the base. So then the concentration of our base would just be the moles divided by liters, which is 0.0667. And so what we need to do then is treat this just like a weak base problem. So we're going to go ahead, make our little ice table here. Have our initial change equilibrium. We have our base. We have our OH minus, and we have our conjugate acid. We're starting with 0.0667 of the base, none of that, and none of that. We will lose some amount of our base, add some amount of OH minus and HB plus, so that we end up with 0.0667 minus x, x, and x. I do need to find KB here, and to do that, I'm just going to utilize Ka times Kb is equal to 1 times 10 to the negative 14. So I know Ka is 4.6 times 10 to the negative 4. So if I go ahead and divide 1 times 10 to the negative 14 by that number, I get Kb is 2.17 times 10 to the negative 11. So not terribly strong, but that's what we expected. The nitrous acid is a moderately strong weak base, and so you would expect its conjugate base to be weaker than it is. So that's fine. So then if we take our values here, we're going to have 2.17 times 10 to the negative 11 is equal to x squared over 0.0667, and I'm going to make the x's small assumption here. We will double check, but it's going to be fine. And if I solve for x, let's see. X is 1.2 times 10 to the negative 6, which if you double check that to make sure the assumption was okay, you get 0.001%. So well below 5%. So we are perfectly fine to make that assumption. And so then the last little bit we need to do here is to work out the pH, because this is not the pH. This is the concentration of OH minus. So what I'm going to do is I'm going to take the negative log of that, and that is going to give me, let's see, 5.92. So that is the pOH. And I know that the pH plus the pOH is equal to 14. So if I take 14 minus that number, I get the pH is equal to 8.08. Which, if I think about it, makes sense, because I have a relatively small concentration of a weak base, and so it makes sense to me that the solution would only be slightly basic. Phew. All right. Now, if you're freaking out right now and thinking, oh my gosh, I just spent like an hour working through one problem. This test is going to be insane. Rest assured, you will not be doing this on an exam. Now, you might do one part of this on an exam, or maybe 2, like if I have you do like the half equivalence point, since that's so quick and easy. Maybe have you do 2 parts, but I will not have you finding the pH at 3, 4, 5 different points along a titration curve on the exam. That's just completely unrealistic. Like, that would have to be the whole exam, essentially. So you will not be doing all of that. I just wanted to do a relatively large example here to show you as much as I could from the different parts there, and show you that it's all stuff we've done before. This weak base, we've done that before. The buffer from the previous section, we've done that before. It's all stuff we've done before. It's just now it's all interconnected instead of being separate sections. So I wanted to show that to you. But again, rest assured, I will not have you doing a 30-minute question on an exam. The most it would be like part B here. Like, I maybe could have you do something like that, where it's just find the pH in this buffer region. And I would tell you beforehand so you wouldn't have to work out what region it was in. So something a lot simpler than that. That still takes a little bit of doing. It's not something you can solve in 2 seconds, but not something that takes you half an hour either. All right, so we will call it there, and in the next video, we will blaze through a few topics here about some different titration curves, some polyprotic acid titration curves, and then indicators. And that will be the last, hallelujah, the last video in Chapter 14. So I will see you in the next and last video in Chapter 14.